Jackie Cation, and welcome to NASA's Universe Unplugged live chat, where NASA scientists are here to answer your questions about our videos, which are the stories where the stories are fiction, but the science is real. Today, we're talking about exoplanets. That's planets orbiting other stars, as seen in our video, the habitable zone Goldilocks Paradox. You can find links to our YouTube channel on universeunplugged.org, as well as all sorts of bonus information and downloads for each of our videos. Now, never miss an episode if you subscribe to the YouTube and go to universeunplugged.org. Okay, so follow us on Facebook as well, because you're probably watching us on Facebook Live right now. Today we're joined by Dr. Jessie Christensen, who's an astrophysicist working at the NASA Exoplanet Science Institute. Her research focuses on the direction and characterization of exoplanets, exoplanet systems, my apologies. And she has a part in NASA's Kepler and the TESS exoplanet discovery missions. Welcome to the show, Jessie.
Thank you for having me.
And we're also joined by Dr. Robert Hurt, who's an astrophysicist at NASA's Spitzer Science Center. He specializes in visualizations of scientific observations, and he wrote and directed the Habitable Zone episodes for Universe Unplugged. Welcome to the show, Robert Hurt.
Always fun to be here.
Let's start the clip from the Goldilocks Paradox before we dive into the questions.
Nice parking job.
From the flight data, it looks like this planet is about 1 astronomical unit away from its star. Just like Earth. That's good news, right?
Oh, sadly not. Since this star is smaller than our sun, it puts out less light and heat. So at this distance, the planet is really cold.
Define really cold.
You ever spent a winter in Antarctica?
No, can't say that I have.
Well, that'd be a tropical paradise by comparison.
Yikes.
An ocean of water is down there, but you can see it's all ice.
That'd be a big fat no on the habitable scale.
I love that show. Anyway, Robert, before we get into the real questions, let's quickly review what we mean by the habitable zone.
Sure. So the whole series is sort of named after this idea, this thing that we define in astronomy as the region around a star that a planet, if it were very much like the Earth, could maintain liquid water on its surface. It's basically just a measure of temperature, right? It's if you're too close to a star, it gets hot. And if you had water, it would boil away and form clouds or vapor in the atmosphere. And if you're too far away from the star, you don't get enough sunlight and warmth to keep the water in liquid form. So it's kind of this Goldilocks zone where it's just on the balance between too much sunlight and too little sunlight. But of course, that also presupposes that you have all the other right fixings for life, or fixings for water on it. So. But yeah, okay. The habitable zone is really just one of those many things that we look for to start characterizing what conditions on the planet might be like. Okay.
And the first planet they visited looked like a big ball of ice. And do you really think there could be frozen planets like this? Jessie, how about you?
Sure. So we absolutely think that there could be frozen planets like this. In fact, our own Earth has gone through periods we call snowball Earth, where the whole Earth froze over, or almost the whole Earth froze over, even though Earth is in the habitable zone. So the complicated part is that the habitable zone gives you one part of the ingredient, that you're the right distance from the star, but there are so many other factors that influence whether you could actually have liquid water on the surface. So we absolutely believe there could be snowball planets out there. We see them ourselves.
So when we plan to go to these planets, we would have to figure out a way to thaw those planets. No? Maybe not? Maybe that seems a little too simplistic? I'll be over here not knowing anything about science. Robert, how can we know how far an exoplanet is from the host star when our telescopes can't image the planet themselves separately from the star?
Well, so yeah, of course, solar systems, we think of our solar system as really big. It takes a long time to get from one planet to another. But compared to the distances between stars, a stellar system is really, really tiny. And even with our best telescopes right now, we can't really get an image of a planet like the Earth next to its star. It's kind of lost in the glare. But one of the techniques that we use to detect planets is if it happens to be lined up just right and the planet moves in front of its star while it orbits, then we can actually detect that little bit of reduction in the amount of light from the star being blocked by the planet. And even though we can't see the planet, that gives us two really important pieces of information. The amount of light that's blocked, the amount of the dip, tells us how big the planet is relative to the star. So we get a sort of size measurement. But then the time it takes for the planet to come around and do it again and again and again tells us how long that planet's year is, how long it takes to go around the star. And knowing what kind of star it is and knowing how long it takes to go around, we can figure out how far away that planet is from its star. And that's great because then that's one of the things we can actually figure out about an exoplanet. And the distance from the star gives us the information we need to know to determine whether or not it falls in that star's habitable zone.
Okay, and I think this question was slightly answered in our last episode of the show, which I think is still on the web, right? We could still watch the previous live chat that we did at universeunplugged.org. Is that right? Yeah, that's right.
Yes.
Okay.
We archiving all of our live chats there. So.
Okay, that's awesome. Okay, so I might go and look at that one again. Now, I have another question, though, is what are some of the clues as to when a planet might be suitable for life as we know it, Jesse?
Right. Well, now I hope I don't say anything that contradicts the previous chat that you guys did on this. But one of the things we're looking for when we're doing this is what we call biosignatures. So these are signatures of what we might call life. So there's biological life. So then we're looking maybe for things like oxygen or methane or liquid water. We're looking in the atmospheres of these planets to see what we can find. At the moment, we don't actually have a smoking gun of exactly what molecule or combination of molecules we could find and point out and be like, yes, that's it. There's life right there. But that's something that we're working on right now, doing modeling, like what is the smoking gun of what we might look for. The other thing I want to mention before we go on is technosignatures. So biosignatures are signatures of biological life. So if we have planets throughout the galaxy that have viruses and bacteria on them, like the sort that are infecting Rob right now, they might emit things like methane or carbon dioxide. But intelligent civilizations might be putting out things we would call technosignatures. So attempts to communicate, attempts to send messages, that kind of stuff. In even our Earth, we have radio leakage, right? There's, if you live 4 light years away, you're seeing our TV signals from four years ago. So yeah, there's all of these different types of things we look for when we're looking for life around other planets.
And you haven't, I would have heard if we would have found life on other planets.
Right. I think there's actually a very strict protocol that scientists would have to go through. I believe I heard about it once. It might be an urban legend, but I think that there's like this protocol that we have to go through if you actually find life on another planet.
Okay.
So now, Jesse, I was going to ask you a question, actually, as a follow-up to that. You mentioned, looking for these biosignatures. Now, there was a lot of buzz recently in the news over Kepler discovery, where people are all excited about finding water in the atmosphere of a planet in the habitable zone. Is beach time? Is it time to go and for a beach party on a new Earth-like planet?
That's right. So there was all these headlines recently about this planetary system. K218 is the name of the star and K218b is the name of the planet. I apologize on behalf of all astronomers because exoplanet names are so bad. But there was this discovery of exoplanet of water in the atmosphere of this exoplanet, and the planet was in the habitable zone. So that's 2 of the 3 things that we're looking for, right? Like water in the habitable zone. But it doesn't have the 3rd thing that we're looking for, which is a rocky surface. Now, we can have a long debate about like what kinds of planets might be habitable, but humans are very self-centered, and we're looking for life like the sort of life that evolved on Earth. And we believe that the life on Earth needed a rocky surface and liquid water and a star like the sun. So K218 has water in the atmosphere. That's really exciting, but it's not habitable, even though it's in the habitable zone. But the reason it's really exciting, I just want to push on this, as we've looked at smaller and smaller and smaller planets, we keep finding water. And that's really promising that if we look at even smaller planets, so K218 is about 8 times the mass of Earth, that's a really good sign that as we keep going smaller and smaller, we'll keep seeing water, and that there are planets like the Earth that have water out there. So that's why I was really excited by this discovery, not because it was habitable.
That's cool, though, is that because if I did not know that about the K planet, which, by the way, you're right about the naming of planets. It's not that hard. I don't know if you ever read Dragon Riders of Pern. Pern was named by the scientists who landed there. It was called Parallel Earth Resources Negligible. That's what Pern stood for. So just make an acronym, scientists. It doesn't have to just be one letter and a number. Live it up. Call it K as in kite, because it flies. Anyway, so we should see if there's any questions online, Facebook Live or the Twitter feed. Are there any questions yet? I'm actually not seeing any. I have some in-depth questions. You guys want to go there?
Sure.
Okay. So in the Goldilocks Paradox, they went to an Earth-sized world in the habitable zone of its star, but it wasn't particularly inviting because it didn't have any water. So this actually, you've kind of answered this, is it really possible for exoplanets to have such a different composition than Earth? Talk about the different compositions that are possible, Jesse, if you would.
Sure. So our solar system is a really good example of this, right? We have 8 planets around our star, and they're all different. And even if you start looking at the moons, then it's even different again. Like if you ask if we have any rocky planets in the habitable zone besides Earth, well, we do. So Mars and Venus and the moon are all rocky bodies in the habitable zone of our sun, and they're quite different. And they all just represent different stages of planet formation. So Venus had this runaway greenhouse effect where its atmosphere just got so thick that it heated up and heated up and heated up, and now it's super hot. No, we don't want to live there. And Mars wasn't big enough. Mars is a little bit smaller than Earth. Mars wasn't big enough to hold on to its atmosphere. So it has a very thin atmosphere, which means it can't trap the heat, which means it's too cold. So this was back to this like Goldilocks zone thing. It's not just the temperature, it's exactly the kind of atmosphere you have. Now, really excitingly, we've been able to look at planets around other stars and look at their compositions. And it's kind of wild what we're seeing. Some of my favorites are, we have this class of planets called hot Jupiters, which are Jupiter-sized planets. So our Jupiter takes 12 years to orbit the sun. These are Jupiter-sized planets that we found right next to the star. So they orbit in only 2 or 3 days. And their atmospheres are superheated to hundreds or thousands of degrees. So one of them, HD 189733b, I'm sorry again, we just put out a really cool...
I know it well.
Alas, poor HD 189733. We put out this series of Travel Bureau posters for interesting exoplanets. And for Halloween yesterday, we just put out this very fun series of planets in the ways that they are spooky and would kill you. So HD 189733 would kill you in just a bunch of different ways. But importantly, what we know about the atmosphere of 189733 is that it has silicates in it, which is like glass. It's thousands of degrees. And the wind speed is 2 kilometers a second, super fast. So what that means is in the atmosphere of HD 189733, it's raining liquid glass sideways constantly. And that just doesn't sound like fun.
No. Next year it could be Hawaii because it'll all turn into sand. But not
don't
yet.
Say that. A whole bunch of astronomers are going to Hawaii next year, so we want it to be nice for at least another 2 months.
Okay. Well, the Earth. What's your favorite planet that you've heard of, Robert? Do you have a favorite exoplanet that you've heard recently?
My favorite exoplanet absolutely would have to be TRAPPIST-1e. I know it's boring to come back to the same one all the time, but in a lot of ways, TRAPPIST-1e is one of the closest analogs we have found to Earth yet. Now, it's orbiting a star that isn't a whole lot like our sun. The star is actually one of the smallest stars you can have and still actually be counted as a star. It's only maybe about 50% larger than Jupiter. And so the habitable zone for that planet is actually much, much closer in. But we know that the TRAPPIST-1e is orbiting, about the right distance from the star to be able to support liquid water on its surface if it's there. And we also know that TRAPPIST-1e is almost the same diameter as Earth. And because of this particular system, we've been able to measure the masses of the different planets in the system because these planets orbit so close together. There are 7 roughly Earth-sized planets orbiting that star, but they're orbiting so close that their gravitational pull on one another actually changes the amount of time it takes to make an orbit. Just speeds them up, slows them down just a little bit, but in a way that we can actually measure, and then through a lot of really careful math, figure out how much mass has to be on each planet to create the amount of gravity that creates the disruption, right? And so because of that, then we actually know the mass. And that's actually something that's really, really hard to measure on planets in general, right? We can see how big they are, but mass, you need to see how they affect something else. And so, yeah, we don't know anything about the surface conditions there yet. It's still a big mystery. So we don't know, if it has water or not. Yeah, go ahead.
Quick question about mass. How does one? What is the? It's a math question. How do you determine mass again? I'm over here with my poli-sci degree. What? How do you do that?
Jesse, why don't you take that?
Sure. So there's two different ways that we use to measure mass at the moment. One is the one that Robert was just referring to, which is the fact that planets tug on each other in their orbits around the star. And if they're more massive, they tug on each other more. And what we see is when we measure the transits of those planets, when they go in front of their star and cause that dip, those dips don't happen exactly periodically like a clock. They come a little early or a little late, depending on where the other planets are. So this happens in our solar system. Jupiter actually tugs on our Earth. And if you were an alien civilization looking and watching Earth transit, you would see that it doesn't actually transit exactly periodically. Jupiter pulls on us forwards and back sometimes. And we can measure the mass of Jupiter by measuring how much it pulls on the Earth. Yay, physics. The other way that we have is the radial velocity technique, which again uses mass. So as the planet's going around the star, we can measure that the star is moving. So the star is moving towards us and away from us as the planet's going around it and moving the star. So Jupiter doesn't just move the Earth, it moves our sun. So our sun is in the middle of the solar system moving around a little bit as Jupiter goes around on its 12-year orbit. So if you're that alien civilization again looking at our sun, you could measure the spectrum of our sun and see that sometimes it's going towards you and sometimes it's going away with a period of 12 years. So you would deduce that star, our star, has a big planet around it with an orbit of 12 years. And the size of the wobble is the mass of the planet. So those are the two ways we have of measuring masses of planets.
Okay. Now, I want to get to a question that we do have actually from Twitter, but let me just tell you, if people have missed the beginning of the show, we're chatting about the science in the NASA video, The Habitable Zone, Goldilocks Paradox, which you can see at universeunplugged.org, or just click on the link in the comments. Universeunplugged.org has a bunch of stuff. So go there, sign up for the YouTube page, and but I do want to ask this question because of the tests. Let me see if I can get this right. So sorry. I'm reading it off the screen. So if NASA, if the test was in orbit around Prox Cent B and you looked in our direction, would you have any idea that the Earth was inhabited or even in that habitable zone? That's a great question.
Right. So the TESS mission is NASA's newest planet hunter. So it follows the model of Kepler, where it's looking for transits, it's looking for these dips that Robert mentioned earlier. So TESS is currently orbiting our Earth and downloading data every month. It's very exciting. Planets coming out all the time. So the question is, if TESS were in fact in orbit around a different planet, the closest planet to us that's not in our solar system, Proxima Centauri B, would it be able to see the Earth? Would it be able to know if it was inhabited? And would it be able to know if it was in the habitable zone? So in its prime mission, that's the original 2 years that TESS was funded to look for planets for, TESS only looks at patches of the sky for a short amount of time. So usually to find planets with transits, we need at least 3 transits, which for the Earth takes 365 days to go around the sun. So you need to wait at least 2 years to see 3 of them. So TESS, as it currently stands, would not be sensitive to planets like the Earth around stars like the sun. So Proxima Centauri inhabitants would not be able to see us. But TESS did get extended recently. So TESS has got another 2 years to go and look at the sky. So if TESS goes back to the original patches of sky that it looked at, it may start to become sensitive to these longer period planets like the Earth. So in the future, it's possible a future TESS, an extended TESS around Proxima Centauri B may be sensitive to planets like the Earth. But TESS can only measure the transit. So the inhabitants of Proxima Centauri B would know the size of Earth, but they wouldn't know anything about its atmosphere, and they wouldn't know anything about its inhabitants. Rob?
Actually, though, we're not actually lined up right for Proxima B, are we? The Earth's orbit, right? Because to see a transit, you have to be. I mean, it's in the zodiac, but you'd have to be like really just aligned exactly correctly, right?
Yeah, that's a good point. So maybe they wouldn't be able to see us with the transit method. There are some planets we know of. Is it the WASP-47 system? There are some systems where we see them transit and they could see us transit. That's kind of cool. And there've been a whole bunch of speculation about how you could use that information to like send messages. Like, could you send a message at a time of transit when you know the other civilization would know that you're transiting? So that's kind of a fun idea to play with. That's a good point. I'm not sure if we transit from Proxima Centauri's point of view.
Yeah, just to kind of pull up a little toy. If this were a star, the problem with transiting planets, right, is that you actually have to also just be lucky, and you have to be lined up in exactly the right way. Because if we had a little planet here, a little quarter that was orbiting this star this way, like around here and here. From our point of view, we're never seeing the planet go in front of the star, so we'd never see the transit. Or even if the planet was orbiting very close to it, we wouldn't see the transit unless it was just exactly lined up to our point of view that we could see the planet pass in front of the star. And so this actually biases us a lot of ways, right? It's easier to detect a planet if it's closer to the star because it's more likely to be in the right angle than if it's further away. The angle has to be just right if it's further away. So it's easier to detect a planet that's large compared to one that's small because a large planet blocks more of the light, so it becomes easier to detect. So there are so many biases in the planets we are able to detect. It really pushes us towards we're more likely to detect big planets and planets that are close in. So once you get to further and further orbits, the statistics, it's very rare to be able to pick something up, say, as far away from its star as Earth is. And if you're trying to pick up something as far out as Jupiter, it's, vastly rarer. So it does mean that even though it's a really powerful technique, for every planet that we detect, there's going to be dozens or hundreds or even thousands more that we didn't detect that are just like it because that system, the other systems just weren't aligned exactly the right way for us to see it. So it's kind of cool. Like in some sense, right, it sets a very lower limit of the total number of ones that are out there to be discovered.
First of all, let me just say, just sitting in on scientists talking to other scientists is awesome. Hi, I'm learning things, and that's really all I think you wanted. So probably not just me, though. So hopefully everyone out there is learning things too.
If we reach even one person, we'll have done our job.
Well, you've reached this one. It's kind of amazing. I have another in-depth question. In the beginning, on the clip, Kara figured out that the kind of star that they were orbiting was by looking at a graph with a bunch of squiggly lines. Is that technobabble, or is that a real way? Is that a real graph on the television, on the show that we just saw?
You're the one who made the plot, Rob. So you tell them whether it's a real plot.
Well, I can tell you that is actually based on real data. I went to an archive of stellar data, and this is one of the techniques, right? We since we can't go to planets, we don't have spaceships that can go to other planets. The only things that we can learn about stars and planets are things that we can access directly. And one of the things we can do is if we look at the light of a star and we pass it through a grating or a prism, we can split its light up the way that you can just run light through prism and you get a spectrum. Now, what's interesting about this is that now you actually get to see how much light is coming out at different parts of the spectrum of light, and that actually lets you see features because different chemistry that's going on in the different chemicals, different elements that are in the atmosphere of the star produces regions that absorb certain wavelengths of light that are emit at other wavelengths of light, and it gives you a very characteristic, almost fingerprint that each type of star has its own sort of unique spectral signature when you break it up into red, green, and blue, and infrared, and ultraviolet. And so, this is the way that we actually identify what a star is. By only looking at how its light appears through a spectrum, we can match that against templates and figure out like, oh yeah, this star must be this big and this has this temperature, and we can connect it ones that we've studied and figure out what the star's properties are.
Okay, so yes, so that graph is based on real data, so that's kind of fascinating. And how about this one? In that video, they could also just look at the planet and see that it did not have any water, that it was all frozen. Is there any way for us to figure out the composition of an exoplanet if we can't see it?
Sure. So we have some information, like Rob is saying. So from the transit, we have its size. And if we can have some way of measuring its mass, like the transit timing variations or the radial velocity that we talked about, then we have bulk density. So for instance, if you have like a bowling ball made out of whatever bowling balls are made out of, and then the same size ball made out of styrofoam, they're the same size, but their weight is very different. So you can start to guess what they're made of based on their weight. And that's what we do. We can kind of classify rocky planets are very heavy and like made of iron and silicates and rock. And gas giants are very light, so to speak, because they're all hydrogen and helium and a few more gases. And then we have the ice giants in the middle, which are more of the heavier elements that would have been ice in the early solar system. They all formed together to make ice. As an aside, I just found out recently that ice giants are not made of ice right now. Isn't that bizarre? They're made of what would have been ice when the solar system formed. I mean, that's just rude, I think. Anyway.
We're always learning.
Yes, we're always learning, even astronomers. So from the bulk density, we can start to guess what it's made of on average. And then we have really clever ways of looking into the atmospheres of these stars. So as the planet is transiting the starlight goes through the atmosphere of the planet. So the upper atmosphere of Jupiter or the atmosphere of Earth, some of the starlight goes through. But then, as Rob was saying, different atoms and molecules have different fingerprints. They absorb light at different wavelengths. So as the starlight goes through the planet's atmosphere, if that planet has CO2 in it, then the CO2 will absorb at this very characteristic wavelength. So what we do is we look at the spectrum of the planet as it goes in front of the star and look for the missing wavelengths. Where are the atoms absorbing, or the molecules? And then we say, aha, so this one definitely has water, which is like K218. That's how they found K218. It was absorbing at this very specific wavelength, 1.4 microns. Or this one has helium, or this one has carbon dioxide. So that's how we're doing it. So we start with this bulk composition, and then if the planets are close enough and around stars that are bright enough, we can get this really exquisite atmospheric measurement.
Okay. And we did get a question from Twitter, which seems very basic, but super, I mean, it's, it feels like the Earth is unique in the universe so far. We've yet to find anything that is enormously parallel Earth, right? Either one of you.
I mean, yeah, every planet, every object that even in our solar system, right, has its own unique characterization, right? There was every reason to think when we sent probes to Jupiter and Saturn that all the moons there would just all look alike, because they must have all formed the same way, and yet like no two moons like even look vaguely like each other around Saturn or around Jupiter, Uranus. So there are so many permutations. That's not to say that we don't expect there are planets that are, exactly, more or less exactly the same size as Earth out there, and possibly even the same composition, give or take. But nothing is going to be, just exactly like us. So, like a snowflake, right? Yeah, Jesse. Yeah.
So just to build on that a little bit, what I wanted to say was we haven't found anything that's exactly like the Earth. But we don't think that's because planets like the Earth are rare. It's because our instruments just still aren't quite good enough yet. So if we extrapolate from the data that we have, which is always dangerous, but we do it anyway, if we extrapolate, then we think that Earth-like planets, by which I mean rocky planets in the habitable zones of stars like the Sun, are common. Now, that's the extent of what we know. We don't know whether they have atmospheres or whether they have tectonic activity and volcanism or whether they have magnetic fields. There's a whole bunch of stuff that makes Earth Earth that we don't have a way to measure yet. But for the very simplest things, rocky planets around stars like the Sun in the habitable zone, we actually think they're quite common.
Okay. And obviously, manned spacecraft to these planets so that we can go look at them. crew spacecraft, because all the peoples, everybody gets to go who has the qualifiers, which then is no longer me. But everybody
it's
qualified.
Be a really long trip. So if you don't think we need comedians, then you're wrong.
True. I think we do need comedians. You might want to bring my album. Hey guys. Anyway, so but the
and anything to help keep us sane on the long trip.
Exactly. Just anything. Yeah, because it's going. How long is that trip? That trip is years, right?
We don't have a way to do that trip yet, is the short answer to the question. I mean, physics is physics, and the speed of light is the speed of light. And science fiction has done amazing things with how to get around that problem, but in real life, physics is physics, and we don't know how to go faster than the speed of light. So if the question is it reasonable to think that we could one day travel to any of these exoplanets, like maybe tens of thousands of years in the future when we've worked out how to do generation ships or hypersleep or something like that? Like, we're not going to be able to go faster than the speed of light that we know of, unless something breaks about physics, which would be amazing, but we can't rely on that. So unless we figure out the technology for generation ships and something like that, in which case we really, really need a lot of comedy albums, then we're then we're not going to be able to travel to them.
And but what's interesting
that's why in Habitable Zone. I was just going to say, that's why in Habitable Zone we do have a fantasy made-up jump drive that lets us take our heroes from one system to another, because we can't do that with today's technology, so we had to come up with a way of letting you kind of look and imagine what these things would be like if we could actually go there.
Right, and if you haven't gone and watched the video, what Robert did with the jump drive, it's just beautiful to look at. So please go and just admire his work doing this very cool jump drive graphic.
Oh, that's cool. And I'd say that so what we're working on now is to create better telescopes. I'm sure there are people that are working on the ships, but astrophysicists are using different telescopes and different sort of like the Mars rover kind of situation to get information closer to exoplanets, right?
Do you want to take that, Rob?
Yeah, there's we keep pitching our telescope technologies, out 10, 20-year intervals, and each iteration we're trying to build telescopes that have more capability to answer questions the current generation of telescopes can have. And with there's a decadal survey that occurs every 10 years, every decade, that's what we call it, decadal survey, where we try to outline what the goals of astrophysics are for the following decade. And one of the recurring themes in this current survey is to figure out what kind of technologies would we have to build to get to a point we could start to identify biosignatures, water signatures on terrestrial type worlds. Because this really is a fundamental question of, can we actually start to find planets that have water on their surface in a liquid form like Earth? And if we can start to find them, can we find any additional hints that there could actually be some form of life existing on them as well? Because this is kind of that big question, right? How alone are we in the universe? Is life exceedingly rare and uncommon, or is it, is there a universe out there teeming with creatures maybe not like us, but certainly mobile and interesting in their own way?
Wow. Yes, I'm very interested in that, as I think is evidenced by the plethora of science fiction that's out there that we're all engaging in. We do have another question, actually. Jesse, can you go more into the ice giants and what they're not ice now? What's happening?
Right. So I'll go a little bit into detail, but remember, this is new information for me as well. So you hear the term ice giant, and possibly you did the same thing that I did and assumed it was a planet made of ice, a very big one. Made of ice, and it's not that at all. So when our solar system formed, it was this big disk of dust and gas, like a big pancake of dust and gas with the sun in the middle. Now, as you get further away from the sun, as we've talked about with the Goldilocks zone, it cools down. You get further out and it cools down and down. Past a certain point, things like water and even CO2, like carbon dioxide, they freeze out and they become ice. So, in the early solar system, there was just like ice dust hanging out in the outer solar system. So once you get far enough away from the star, when you're building planets, you're building them out of things that were ice in the early solar system. But what they are now, So they have these thick atmospheres. So I'm talking about Neptune and Uranus. They have these thick atmospheres because, you know, we see the great blue spot on Neptune, which is the equivalent to the great red spot on Jupiter. But inside, as you get in, it's this super dense. The pressure is so high that it's this super dense, like super ionic ocean, they call it. It's so dense that the gas is just compressed down into this like super dense liquid that's, you know, thousands of degrees. So, you know, again, you find liquid, but it's not the liquid you like. So yeah, this was all brand new information for me as an exoplanet scientist. I was like, wait, tell me more. So it was really exciting.
Okay, and can you want to name the cool upcoming telescopes that I don't know the names of?
Sure. So just to build on what Robert was saying, because there are some really, really cool ideas and even, you know, telescopes being constructed right now to look further into planets, and especially planets like the Earth. So from the ground, we have the Giant Magellan Telescope and the 30-meter telescope and the extremely large telescope. That's literally what it's called, the extremely large telescope.
We're so good at naming things
at this point. So those are ginormous telescopes, so 20 meters, 30 meters, 40 meters that are being built on the ground in order to in one of the science cases is to look at extrasolar planets. And that's to do imaging. So we've talked about transits and radial velocity, but there's another way, which is the most obvious way if you think about it, which is just to try and take a picture of it. So we come up with this very cool instrumentation which tries to block out the light from the star and look for the planets. So these telescopes are designed to do that. And that's technology we can do on the ground right now. But we're already thinking ahead. What are we going to be able to do in 20 years? And then in 20 years, we're going to go to space. So part of the decadal survey was we scoped out some of these big space missions that might be able to do this, to actually image planets like the Earth around stars like the sun, around nearby stars. And so there are these really amazing concepts that people have come up with, fantastic technology that we don't quite have yet, but we have a roadmap to get to. And that'll be amazing. We'll be able to launch these big telescopes and see Earth-like planets around stars around the sun, stars like the sun. So that's very cool. But 20 years from now.
Fair enough. It's this has been amazing. We're pretty much done with the live chat, you guys. So thank you, everyone who joined us to learn more about the science of the universe Unplugged video. Go to universeunplugged.org and you can watch all of the videos that Robert has made. I'm so sorry. The Habitable Zone, Goldilocks Paradox.
And videos that I didn't make too. We have lots of videos.
And exactly. There are plenty of videos. Robert isn't making all of them, but he's made some good ones. And so you can see that and all the other Universe Unplugged videos at universeunplugged.org, or just click on the link in the comments. Subscribe on YouTube. You'll be the first to know when our next video comes out. And follow us on Facebook to catch our next live chat. Until next time, I'm Jackie Cation, and this has been Universe Unplugged Live Chat. Thanks, guys.
Bye.
See ya.